Bismillahirrahmanirrahim. Good evening, everyone. Welcome at new lecture. Today, I will try to solve two questions at that same video. Like I said before, I depended on these two sources, semiconductor physics and devices, and the second one is solid-state electronic devices. Okay, this question, Atlas chapter 3 and 4, all these questions I selected it, Atlas chapter 3 and 4. Okay, let's start to solve these questions. At first, I want to introduce myself. I'm Ali, I'm a master student in Mullah University. Let's go to solve this question. Here we're dealing with silicon at room temperature. N naught, that's mean the concentration of electrons at conduction band equal to dot exponential 5. Sorry, requirement A, determine the position of the Fermi level with respect to the energy valence levels. Determine P naught, and the last requirement is ask us, is this N-type or P-type materials? Actually, this question is easy, but question number 10, it was difficult and important at the same time. Now, like I said before, we're dealing with the room temperature and not the concentration of electrons at conduction band equal to dot exponential 5. We're dealing with the same unit. When we have this equation is important because asked us to determine the Fermi level with respect to the energy valence band, that's mean EF minus EV, equal energy band gap to silicon at room temperature, we know it, equal 1.5 dot exponential 10 minus the difference between valence band to the conduction band here. That means this will be the main equation to us to depend on it to solve this question, to solve requirement A, sure. Okay. Here, we know the result of EG at silicon at room temperature. After that, we must find EC minus EF to can solve and calculate the last result of EF minus EV. Here, like we know, the difference between the conduction band from the valence band equal KT ln effective density at the conduction band divided on concentration of electrons. K here is the Boltzmann constant, equal 8.61 dot exponential minus 5 EV divided on Kelvin. Let's complete. Let me delete all of that. Yes. Here, we're dealing with N-type doped. That's mean N naught equal ND equal to dot exponential 5. Okay. Now let's solve this equation. The last result to this bracket, KT, like I said before at the last lecture, equal dot 0.289 ln 2.8 exponential 19. This the NC, the effective density at room temperature, something like constant. We calculated before, divided on, like I say, 2 exponential 5. The last result is dot 843 electron volt. After that, we must put this results here to can calculate the requirement A. That's mean here EV minus EF, the Fermi level, minus EV, the valence energy band, equal dot 277 electron volt, the position of Fermi level with respect valence band. Okay. Now, let's go to determine at the requirement B, determine P naught. P naught, that's mean the concentration of holes at the valence band. Like I said before, we're dealing with N-type. N naught is the majority, P naught the minority. That means the author wanted from us to calculate the minority here, minority hole at the N-type dot. A thermal equilibrium concentration of holes in the Fermi level, P naught equal NC, the effective density at the conduction band, exponential minus Fermi level, between two brackets, sure, Fermi level minus valence band divided on KT. Like I said before, because the temperature is room temperature, this KT, we calculated it before, equal 0.0259. Okay, and NC, like I said before, we calculated it before, because we're dealing with room temperature. If the temperature is different, we must calculate NC and NV by ourselves. Okay, now we have the result of effective density at the conduction band, and we know the last result about this bucket KT. Okay, but we don't know what this equal. Oh, sorry, let me do that like this. Yes. Okay, let's complete. Yes, I don't know why. Yes, no, yes. The last result of the concentration holes at the valence band equal to 0.41 for 414 dot exponential 14 to the same unit, the thermal equilibrium concentration of holes. If the author didn't say we're dealing with thermal equilibrium, you know how we can calculate P naught and N naught. Totally 100% we will dependent on the mass law, N naught, P naught equal intrinsic carrier concentration square. Okay, now let's take a look about requirement C is the N type or P type. By this situation now, we have the two important results to us to can solve this requirement. We have the result of P naught and we have the result about the constriction electrons. Now let's do comparison between these two results to know which will be the bigger one to can depend on it and answer this question. Here P naught 2.414 is bigger, dot exponential 14 is bigger than 2 dot exponential 5. Sure, is the big difference between them. That means we're dealing with P-type dots. Okay, now let me take a breath and go to solve this important one from my lectures at this week. At requirement A, the author gave us this result, the Fermi level minus the difference between Fermi level and the conduction band equal 0.28 electron volt. But in germanium arsenide, now we're dealing with another element, not with silicon at all. Let me put that, yes, with germanium arsenide. Now we don't dealing with silicon at all. That means we have another energy band gap, we have another effective density of conduction band, another effective density of the valence band. Okay, and the big disaster is, let me use the red pencil. The disaster, the temperature is 375, not room temperature at all. Calculate the value of the constriction hole electrons and constriction of holes at the valence band but at thermal equilibrium. When we saying thermal equilibrium, that's mean we will depend on another equations, will not depend directly on the simple equation, I mean mass law and not P naught equal square intrinsic carrier concentration. No, we will depend on another equation, more complicated equation, okay? But no way. Without these questions, without these equations, we can't solve questions like that. At thermal equilibrium, okay? At room temperature, like I said before, at thermal equilibrium, electron concentrations, and not in the conduction band, and not equal. Let me see this equation. I didn't write it here. The original, the main equation. After that, we will go to the center this topic. And note, concentration of electrons at the conduction band equal NC, that means the effective density exponential minus C, EC conduction band minus valence band divided on KT, okay? But here, if we say a note, I can write a note dealing with room temperature, but here we're dealing with another temperature, 375. It's different from room temperature. That means when I was thinking with myself, I thought why we don't put dash on this concentration electrons of holes to can do compression, to can make this topic easier to us to because when I see the dash on the N naught or P naught, I will know we're dealing with something different. Okay, here and dash here I use it this dash because to show now I'm using with another temperature, not room temperature at all. Okay, because that I used dash here, and not dash and concentration of electrons or new electron concentration at the conduction band with another temperature equal effective density. This is the disaster here. NC is the effective density at the conduction band, but at not room temperature. That's mean we have another result here. We must calculate it again by ourselves. Okay. Let me show that. Here is different. At the same time, EC minus EV divided on KT. Here, the T is different. That means we must calculate this bracket again by ourselves. Let me delete after all that and go complete our solutions. Yes. Here, don't equal 2.81 dot exponential 18 anymore. We must calculate it by ourselves. By ourselves, we have complicated equation. Effective density of conduction band equal to between two bracket 2 pi effective mobility of electrons. KT, that K here, it's the Boltzmann constant. T divided on Planck's constant to force 3. It's complicated. If I can avoid this complicated equation or complicated calculation, that will be easier to us because that I will use another math trick. This is easier to us. I can take some benefits from this equation, from this relation, because actually in physics science, effective density has a relation with the temperature, but to force 3 divided on 2. Because that, when I have, let me show that will be clear. I have NC1, effective density at room temperature. That's right. And I have temperature 1. It was the 300 room temperature. It's equal 300 Kelvin. T2, the author said it to us 375. That's mean this relation we have 3 results. This By using all these results, I can calculate the new effective density at conduction band. Let me delete all that. Here, NC2 equals 6.557 dot exponential 17 to centimeter to force minus 3. Okay. Now, we found it. KT, we must calculate it because here T is not 300 Kelvin. Boltzmann constant equal 8.61 dot exponential minus 5, or in another source maybe you will see 0.861 dot exponential minus 6. That's the same. The unit was electron volt divided on Kelvin. Okay, because that's here the last result will be just EV, because the Kelvin here will disappear with the Kelvin here. Okay, let me complete. Yes. Now let's calculate the difference between conduction band minus valence band. The last result is 0.28 electron volt. I'm sorry, this is from example. The author gave it to us to help us to calculate the other. Now, and note dash, that's mean the new concentration of electrons at the conduction band with another temperature. Okay, here NC, like I said before, here equals 6.57 dot exponential 17, and now we have the twice results because here I calculated what this bracket is equal here. Dot 0.323 electron volt, and EC minus EF. We have this result. That means the concentration of electrons in the conduction band at thermal equilibrium equal 11.52 dot exponential 13. Let us use this. Okay. Now another at the same requirement or another requirement I didn't know, I can't remember. The author wanted from us the concentration of holes at the thermal equilibrium. Let me delete that and complete. Okay, the concentration of electrons in the valence band here, no, here the concentration of holes. This is not right. The concentration of holes in the valence band and thermal equilibrium, P naught dash the new concentration of holes at the valence band equal NV2, the effective density at not at room temperature, exponential minus the difference between valence band minus the Fermi level minus the valence band divided on KT. It complete. Okay. Here we must find the result about NV because we don't have its result. Okay. We have the result about just KT because I calculated it before. And we don't have the result about EF minus EV. Okay. By using the same relation, the same equation from this equation, okay, NV2 equal 9.78 exponential 18. By that, now we must, let me disappear, make this disappear, okay? Now we must calculate the difference between Fermi level minus a valence band to find the last result about the new concentration of pulse at the valence band. Now, by using this relation, it's important, we will use it more and more at the next questions. EF, the Fermi level, minus the valence band equal KT minus EC, the conduction band, minus the valence band. Okay. Here, at the for germanium arsenide, energy band gap equal 1.42. That means we have this result. Okay, minus, yes, and EF minus EC minus EV, we didn't calculate it. Let me disappear all that again to come move. Yes. Here, P naught, the new concentration of holes at the valence band equal, the last result will be here, 4.988 at thermal equilibrium. By calculate when we note the result between EF minus EV, I mean the last result to this bracket, we can use it directly to find the new concentration of holes. Okay. Now we want from us calculate the difference between the conduction band from valence band, but at room temperature, and calculate the concentration at holes at the valence band. Like I remember, it was about the room temperature. Yes, assuming the value of concentration of a hole electrons in part A remains constant, determine the difference between conduction band minus valence band, and calculate the concentration of holes at room temperature. Here, that will be easier to us because we solve many questions like that. Here, N naught equal 11.52 dot exponential 13. Here, to find P naught, we must find N concentration of electrons at the conduction band at first. To can use the mass law to can calculate the P naught. Or don't use the P naught, we can use this another questions, but that will be necessary to solve it, or not solve it, not to take the benefit directly from this equation, but when we know the relation, when we know the result about N naught, the concentration of electrons, and NC, the effective density at room temperature, we calculated before, here we calculated before, we can calculate the result about the difference between conduction band from valence band, because that will be necessary to can solve another questions to find the difference, to find here, because EF minus EV, it's we don't have this result, because that I will use this technique to find the equation to this bracket. Just we will divide concentration of electrons divided on effective density at room temperature, and after that we will take length to the both side, and we will delete this minus by put the effective density above, up, and concentration of electrons down. Okay, by that we could calculate this bracket, conduction band minus valence band equal 0.0259. Okay, and here electron volts, I'm sorry, the last result here 0.215 electron volt. For germanium arsenide, like we know, energy band gap equal 1.42 electron volt. Here at thermal equilibrium, let's calculate the P naught like the Arthur wanted. P naught at thermal room temperature equal NV exponential minus EF minus EV, the valence band divided on KT. Here, we know this result. Sorry, I don't know what happened. We have this result, effective density at the valence band, because we calculated it before, equals 7 dot exponential 18. But if the temperature will different, that's mean we must calculate NV effective density at the valence band again with the new temperature. Okay, we calculated before with room temperature equal .0259. Now to calculate the difference between valence band from the Fermi level from the valence band, we will use this result. Okay, because the difference between Fermi level from the valence band equal K energy band gap minus EC, the conduction band, minus Fermi level. Let me put this around it. It's important to us. We will depend it to solve many questions like that. Now, when we found it, the result about this bracket, Fermi level minus valence band equal 1.255 electron volts. We can calculate this result because now we know the result about NV effective density at the valence band with room temperature, because we calculated it before. Here we calculated it before, and with this bracket, conduction band minus valence band, we could calculate the difference between valence band minus energy Fermi level minus energy valence band. Here, the result about the concentration of holes at thermal equilibrium equal 0.0436 centimeter to force minus 3. That's it. Our lecture today is done. It's finished. Thank you for your watching, for your listening, your patience. Yeni derste arkadaşlar görüşürüz. Kendinize çok iyi bakın. Eyvallah. Let me stop recording.